Alright, this is going to be the lecture video for Chapter 10, Rotational Kinematics and Energy. So we are now going to start rotational motion, which takes aspects of almost everything we've talked about, except we're going to put it with objects that are rotating or going around in circles. So you still have position, velocity, and acceleration, but now we're just going to call them angular to reference that our object is rotating. The basics of rotational kinematics, the similarities between linear and rotational quantities, rolling motion, and then rotational kinetic energy and the moment of inertia, and then conservation of energy for objects that are rotating. So first and foremost, you have position, velocity, and acceleration for rotation. For angular position, we are now going to represent this as theta, which is the angle measured from the reference line. So wherever you decide your reference line is as the start to where the object stops rotating, that's theta. You measure theta in radians, which is dimensionless. It's not x or y, right? It's on a curve. If theta is bigger than 0, then you have counterclockwise rotation happening from the reference line. If your theta is less than 0, then you have clockwise rotation from the reference line. So when you talk about angular position, sometimes they will make references and measurements either in degrees, revolutions, or radians, theta. Radians is the proper units, but sometimes you will need to convert between degrees and revolutions and radians. So one full revolution is 360 degrees, right? It's a circle. One revolution is also equal to 2 pi radians as well. We also talk about arc length. So this is measured in radians. So this length, right, however far it rotates, we can say that it's the radius times theta. We also have angular velocity. So instead of v for angular velocity, you have omega, which looks like a little w. It's a Greek letter. So just like normal velocity, it's the change in position over the change in time. Except this one is change in angular position over the change in time. And our units for angular velocity is radians per second. So radians is for position, so radians per second for angular velocity. You can also have instantaneous angular velocity. It's the limit of the change in angular position over the change in time, still measured in radians per second. If your angular velocity is positive, then you say it's going clockwise. If your angular velocity is negative, then you say that you are going clockwise. Alright, then we have period of time. So period of time is how long it takes your object to revolve once, to do one full rotation, to go around in a circle once. And we represent that with capital T. So it's still T, it's still time. So you do that by doing 2 pi divided by your angular velocity. And since it's a time measurement, it's still measured in seconds as well. Then we talk about acceleration. So the book has a mini typo. This is not velocity. This is angular acceleration. Angular acceleration is represented by alpha, right? A Greek symbol, kind of looks like a little bit. but it's the change in angular velocity over the change in time. So the units are radians per second squared, similar to your kinematic ones. Alright, so just like velocity, we can do instantaneous angular acceleration. So taking the limit as change in time approaches 0, change in velocity over change in time, still measured in radians per second squared. So same similar concept, just uses a little bit of pre-calculus to find the same thing. But if angular velocity is greater than 0 and angular acceleration is also greater than 0, then your overall angular speed increases. If your angular velocity and angular acceleration are both less than 0, then you also say your angular speed increases. It's just going in a different direction. Versus if your angular acceleration is greater than 0 and your angular velocity is less than 0, well, now they have different signs. So you say that the speed decreases. And just like in example D, they have opposite signs, angular speed is going to decrease. This is just like with regular kinematics. If your velocity and acceleration have different directions, your speed is going to slow down. If they both have the same direction, it's going to speed up. Same exact concept here as well. So we are also going to assume that acceleration is constant for rotational motion. So that means you can find final angular velocity is equal to initial angular velocity plus angular acceleration times time. Just like your regular kinematic formulas. The only difference is they just have the Greek symbols for angular quantities. So this is a really, really good comparison chart. Like, I would recommend you have this as part of your formula chart, but it gives you comparisons of linear motion to the angular motion quantities. So x is position, angular it's theta, v is velocity, angular it's omega, a acceleration, alpha. And all of your kinematic equations that you did a few chapters ago have the same counterparts for angular. All they did was change the variables to these guys. So the equations really haven't changed. They're exactly the same, just with rotation. All right. So with rotational motion, you can also find the tangential speed, which means the speed that's tangent to your circle. So right up against the circular path here. And all you have to do is when you convert, you just take your radius and you multiply it by your angular velocity. And then this becomes linear again. So it goes back to meters per second. So that arc length formula that was at the beginning of this lecture video, right? It's the same concept. Arc length is measured in meters, and you take your radius times the angular displacement. You can also find centripetal acceleration. All right, so we talked about centripetal acceleration a little bit when we did circular motion with forces. So you just take your radius, multiply it by your angular velocity squared, and you get your centripetal acceleration that's going to pull towards the middle, towards the center. Tangential acceleration, right, converting back into linear, is the same process. Take the radius, multiply it by your angular acceleration. Then you go back to meters per second squared. And then this is just comparing the two. So tangential is just due to a changing angular speed, right? This is on the outside of your circle. It's tangent to the path. Centripetal is due to the changing direction of motion. So it's pulling towards the center. So here's a really good picture that shows both. So here's your tangential acceleration. So it's tangent to your circle. Then you have centripetal that pulls toward the center. And then the overall acceleration vector is in between the two. Right, so rotational motion deals with objects that roll. So if you have a normal round object that rolls without slipping, so it rolls, there's no hiccups or anything, you have a fixed relationship between the translational and the rotational speeds. So just like you could find tangential speed with radius times angular velocity, you can also use this formula over here, where if you just have the period of time and the radius, and you didn't have angular velocity, you could find tangential velocity too. And it's just taking 2 pi r, which this is the circumference of the circle equation, and divided by the period of time that it takes to go around once. So you can also consider rolling to be a combination of pure rotational and pure rotational motion together. So not only do you have your tangential velocity, you also have angular velocity happening. So it's just both combined into one. So if an object is rolling, it makes sense. Energy. Just like kinematic formulas for motion, kinematic energy, right, regular energy that we studied before, can be translated into rotational motion. So for kinetic energy, we know for linear that it's 1/2 times mass times velocity squared. Great. We now have to add into account that your object is rotating. So total kinetic energy of an object that is rotating is that linear kinetic energy plus 1/2 times mass times the radius times angular velocity squared. Then if you simplify, you get this guy. You can also write rotational kinetic energy as I times angular velocity squared, where I is something called the moment of inertia. And it's similar to mass in the rotational world. So you take the mass of your object times the radius of it squared. Different types of objects have different ways to calculate moment of inertia. And you do not have to memorize these. I would add this to your formula chart. But depending on the type of object, it tells you what the moment of inertia should be, how it relates to mass times the radius for different types of objects. So don't memorize these, write these down to add to your formula charts. So when you take into account linear motion and rotational motion for kinetic energy, you just need to combine them together. This second equation down here just makes it clear that you have different kinetic energies at play within the same object. So most commonly you will see it as this guy. But this just tells you have linear kinetic energy and rotational kinetic energy happening at the same time. So one example is you have two objects. One is solid, one is hollow in the middle. They have the same mass, the same radius. They're released at the same time. The disk is going to reach the bottom first because you have more of its gravitational potential energy becoming translational kinetic energy and less rotational.